Everyone, this video is divided into two parts. In first part, I will show you how to package your HDL code in an XC wrapper and create an IP out of it. This is useful if you want to interface your hardware with a Zinc processor or a Microblaze soft processor. So I will create a simple adder that adds two numbers and create an IP out of it. So this is how I will do it. So first I will create a new project. Let's call it simple adder and I will put it here. I'll be using the ZC104 board. I've already written down all the codes so that it will save some time. So this is my module. Simple module, it takes two numbers and adds them. So this is the hardware. So now how to package it into an IP. So for this we go to tools, create and package new IP. Next. So first we create this create AXI peripheral. Next. So let's give it a name my IP simple adder and select a folder. So this IP will be stored in the folder IP repo. So now here we need the data width is actually fixed to 32 bits. If you want to make a 64 bit IP, so you need to write the XA interface codes from the scratch. So Vivado does not generate XA IP with 64 bits data width. So number of registers. So currently we have three: A, B, and output. So we need at least three registers. So let's take four itself. There will be four registers. Here we will select edit IP and click finish. So once this window opens, click on review and package and then repackage IP. We don't need to do anything here. So now we go to the same folder, desktop demo IP repo. So from here actually we need only two files. These two. These are the XC wrappers. So we just cut them and in our simple adder sources, source one, with our adder demo code we paste them here. And now we can just delete this folder. So we will create another folder. So in this folder we will store the actual IP. So now what we will need to do that we need to import those two files. So we do add files. copy sources into the project state and click finish. So now you can see we have these two files. So this is the one file and this is another. So this is the top level file. Currently this is a simple project and generally we don't need to do anything to this file. This file instantiates the other file inside it, and in the second file we will instantiate our own hardware. So we will go at the bottom. You can see add user logic is shown here. So here we will instantiate our module. So our variables are a, b and out. A, b, out. So if you remember, we have taken 4 registers in this AXI wrapper. So these are the 4 registers: SLV reg 0, 1, 2, and 3. So let's assign SLV reg 0 to A, SLV reg 1 to B, and now we just can't write SLV reg 2 here. So one thing to remember is these SLV registers, these SLV registers that are in this file, these these are all these all take input values. So if we want to have output values, we need to define new variables. So let me just check out where to define them. Okay, so here the 4 registers have been defined 0, 1, 2, 3. So we will consider SLV-2 as the output register. So hence we will declare the output variables here. And also note that we have to change the name. We are not touching this register, just leave it as it is. The SLV-2 we won't be using it. And note that the output has to be wire, otherwise it's a rule of Verilog. The output can only be connected to wires, not registers. So we will take this SLV-2 out and paste it here. And also note this reg data out, we will make this here 2 out. So this declaring of these output variables you have to do for all the output signals that are present in your code. So currently I have only one output. If there were 10 output signals, I have to declare these 10 registers separately. So once this is done, I will run the synthesis to check if there are any errors. Okay, so the synthesis is complete without any error. We can view the reports. Here we can see that we have viewed only 1% LUT, 1% flip-flop, 1% VRAMs, and 24% IOs of this FPGA. So once this is done, now we will create the IP, actual IP. So we will go again the tools and create and package new IP. This time we will select package your current project. And the folder, we will select that new folder that we have created. Simple adder IP. Next. So once this is loaded, we will again go to review and package IP and click on package IP. Now this time in our IP, this adder demo is there. So we have created our IP. Now we will close this and create another project. So we are done with the first part of the project. Now we will start with the second part of the project. That is, we will interface our IP with a Microblaze processor. So first we will create new folder. We will select this folder as our destination and give this itself as a name. ZC104 is our board. It does not matter what FPGA board is using. So we go to go on creating a block diagram. Let's give it a random name like design 101. Okay, so first we will tell this project where is our IP. So we will go to tools, settings, IP, repository, and if you remember we have stored our IP in this folder, simple adder IP. We will select this and you can see that the IP has been recognized. We will click on OK. So now like if we search here my IP, so you can see that our IP has been recognized. So first time we will add the Microblaze processor. And block automation. Make this 128 KB. Okay. So now we will again click on connection automation and let it make these connections. We will change some of them later. Okay, so this is done. Next, we will add a VRAM controller. Again, run the connection automation. And just remove this and make this new VRAM block generator. Then again click on connection automation and this for the second port. Select the previous VRAM that we have created this one. So one more thing that is remaining to be added here is our IP. So we will add our IP and do the connection automation. Next we have to add UART. UART is necessary because when we do printf and all, the data comes through the UART. And we have to add this UART light, not UART 16550. We have to add UART light. We will do the connection automation. This is our UART. In this we have to make some changes. This baud rate should be 115200. The whatever test bench we have written, this is specifically for this baud rate and frequency of 200 megahertz. So the input and output clock frequency of this clock wizard should also be 200 megahertz for our test bench to run here. So we will remove this 300 megahertz pin, delete. Click on this. We will make it custom. Clocking option. We will make it manual and feed here 200. In the output clock also, we will make 200. Do OK. And then we will right click here, right click on the clocking wizard and select make external. And then we will verify the design. So validation is successful. So this is our entire Microblaze design. And also note that the reset yield here is active high. We can close it to create the ideal wrapper. Copy generated wrapper to allow user edits. So this is our wrapper. So next we need to do is run synthesis. So it will take some time. So finally the synthesis is complete. We can do view reports. Here one thing to note that I have moved my demo folder from desktop to root of C drive. C drive, here demo. So I had to do this because sometimes the file folder paths become so large that it creates a problem. And this is a limitation of Windows. This does not happen with Linux. So anyways, we can move on. So next we will do is find, export hardware. We don't want to include bitstream and just click on OK. Next again, file, launch SDK. So this design 101 wrapper hardware platform 0 is our imported hardware. We will now do file, new, application project. Just give a name. Some test. We click on next. Now note that when you are selecting hello world, we can click on finish. But had we not included the UART, we won't be able to create a hello world project. So this is our hello world.c file. In this, I would like to focus on two header files. First, let me just copy paste the hello world.c that I have already written. See xil dot underscore io and x parameters. So xil underscore io has the definition of the function xil out 32, then xil in 32. So these are basically xil out. By using xil out 32, we send data to our hardware, adder hardware, and by using xil in 32, we receive data from adder hardware. And the next is x parameters. So x parameters is present in the BSP folder. So this file contains the base address of all the peripherals that has been used to make this hardware run. So our hardware will be at the end. So this is our hardware. X per myip simple adder. I will just copy this base address and paste it. So I pasted everywhere. And note that to address 0, we are sending the first operand. To address 1, we are sending the second operand. And at address 2, we are reading out the result. In this project, we have not created any signal that would show that our result is ready. Hence, I've given a delay of 1000, or we can just make it 100, or let it be 1000 only. One more thing to note that when we will be running this code in simulation, not in actual hardware, the exile printf takes a lot of time. So we need to be patient. So next we will build the project. So build is successful. And if we go to SDK, our project, some test, debug, we can see that the ELF file has been generated. So we can close this and move on with the writing the test bench. Simulation sources. So this is the code of my test bench. I will just copy it. I will select the language as VHDL because the test bench is in VHDL. So the main thing in this wrapper is the UART, reading the signals that are coming out from the UART, and this works only with 200 megahertz clocks, as has been mentioned here in the comments for your reference. Both input and output clocks of the clocking wizard should be 200 megahertz that we have done, and this entire code, the state machine, is just for reading out the output from the UART. So after this test bench, we have to associate the ELF file. So we'll go to tools, associate ELF files, the second one, add files. This is presented. Let's see. Then your ELF file. And click on OK. So you can see the ELF file is here. And note that the properties look like this. Relative first, the path mode should be relative first. So now we can run the simulation. So once this launches, just press on run and let it run. One by one you can see that the outputs will be coming in the TCL window. I will not fast forward this screen so that you can see the actual time that it takes to for the output to appear. So we can see that our first result is here, 5358. Let's see if it's correct. So this was my hello world. We have given the inputs at 1876 and 3482. So 1876 plus 3482 is 5358, which is correct. Let's wait for the second result. So the next result has come out to be 13521. Let's check it again. 7893 plus 5628. So 13521. So our result is correct. So the third result of course will again come out correct. I will pause the simulation. So this is how you can run C codes even if you don't have an FPGA using Microblaze soft processor. Thank you.